I want to explore these ideas a bit more and talk about what's called formal charge. All right, well, so let's take a look somewhere else. Let's say, how many resonance structures does CO2 have, carbon dioxide? And, we don't have the Lewis structure here, so we'll come up with it. We start with calculating our total valence, make our skeleton, do some accounting, make our lone pairs. All right, and this is, when we make those lone pairs, we've now used all of our electrons, and carbon doesn't have an octet. So we know we're going to have to make double bonds, or that's a good sign. Hey, I'm going to make some double bonds. We formed this before. So hey, we made our CO2 Lewis structure. This is what we're used to seeing. But we still had a choice when we made those bonds. And whenever we're going through Lewis structures and we have a choice to put in double bonds or make double bonds, that's always going to be an indication of the potential for resonance. Because, I formed two double bonds, but I could have chose both my lone pairs on one oxygen and done a triple bond and a single bond. Right? I could have done that. Why didn't I do that? What's the difference between the double bonds, and what's the difference between those? And so on face, it would look like I have three different resonance structures for carbon dioxide. And when it comes down to these are different structures, right? In one case, now I have triple bonds or single bonds, right? And that's going to be different. There's going to be some mixing here where I didn't have that before. And so I've changed what's going on. Right? Am I mixing singles and triple bonds? Are there double bonds? What's all going on? And so, normally we don't talk about resonance with CO2. And so that's because when we have these varieties of different structures, one of them is going to be called the major structure. So one of them is the actual representative. Right? It's not, we have different choices. Our resonance structures are not all just kind of interchangeable. They are distinct. And as a result, one of them is what we can think of as the best. One of them is the representative major structure. And it's not, these different resonance structures are not mixed together. It's instead just mostly the single Lewis structure. And that Lewis structure is representative. And so this ends up being the major structure as we would think. Right, so the reason why we're going to look at CO2 as our example is because we know what the answer is. So let's see if we can figure out why this is the actual Lewis structure for CO2. Why CO2 is not a mixture, it's just this one Lewis structure. And so the questions we can ask is, we can start to think it's bonding. Well, how many bonds does carbon tend to form? Well, carbon has 4 valence electrons. It needs 4 more, so it's going to tend to form 4 bonds. And in all of my molecules, carbon's forming 4 bonds. So far so good. Can't really distinguish them. What about oxygen, though? Oxygen has 6 valence electrons. Oxygen atoms tend to form 2 bonds. And here's where we can see that central structure. Each oxygen atom has 1 double bond. That's right along what we would predict for oxygen. Whereas the other structures include oxygen with a triple bond and a single bond. So that is not necessarily what oxygen prefers. Yes, it has an octet, but it doesn't really have the right octet, if you will. And there's a different arrangement of electrons where everything has the right octet, but everything's following the expected bonding patterns. So what we want to do is come up with a way to kind of characterize this distribution of electrons in a single molecule. Well, one of the things we can think about is, well, we have electronegativity, right? This is a property of atoms in molecules. And does this work? Can we use this? And it's going to be relevant, but it's not going to be the whole answer, right? Because electronegativity just tells you that atoms, want more electrons within a bond, but it doesn't tell you necessarily what type of bonds they're going to form or anything like that. So electronegativity is going to be important for determining major structures, so we don't want to forget that. But we need something else. We need to define a new property of atoms in molecules. To this end, we're going to define what are called formal charges, which we're going to abbreviate with FC for formal charge. So the formal charges, the idea, it's a fictional charge. Okay? And so this isn't a real charge or anything. What we're going to be doing is looking at assigning a value to individual atoms within a Lewis structure. That's going to be a way to characterize, does this atom have this right valence? Is it forming, does it have the right distribution between bonds and lone pairs, right? 8 is just the number for the right number of electrons. But formal charge is going to say, is it close to having the right distribution of basically bonded electrons and non-bonding electrons? And so overall, the idea is it's basically going to be a counting of, do you have too many bonds? that's going to give you pluses, formal charges, or too few bonds, that's going to give you a minus, kind of the right, not the right number of electrons. So our overall equation for formal charge is the atomic valence. So it's each atom, right? So if we say, oxygen, we'd put a 6 there because that brings in 6. If it was by itself, it would have 6 electrons. We minus the total number of electrons associated with that atom that are lone pairs. And then we subtract half of the total number of electrons associated with that atom that are in bonds or shared electrons. So if we look at an example of phosphorus trichloride, right, we've taken a look at this Lewis structure. We're going to have a formal charge for each type of atom. So phosphorus has 5 valence electrons, right? So that first thing is just going to come from the periodic table. All phosphorus, always going to start with 5. It doesn't matter what its Lewis structure is. But then we take a look at the lone pairs. So the lone pair, 2, corresponds to the 2 right there. Then we can see that it is in 1, 2, 3 bonds. That is 6 total bonding electrons. So minus the 1/2 times 6 for the 3 electrons that basically it contributed to those bonds. And so we can see that the formal charge for this phosphorus in this molecule is 0, right? Because it's 5 minus 2 minus 3 gives it 0, because phosphorus tends to form 3 bonds and have 1 lone pair, giving it a formal charge of 0. Everything is lining up. Each of the chlorines brings in 7 valence electrons. They all have the 6 electrons from the 3 lone pairs, right? Those 6 dots around each chlorine. And then they each participate in 1 bond, which is 2 electrons, so the 1/2 times the 2. Again, the chlorines all have a formal charge of 0, because chlorine tends to just form 1 bond and have 3 lone pairs. So that would mean these atoms follow the expected bonding patterns. You will notice this is different than oxidation numbers. Oxidation numbers are a similar idea of assigning charges to atoms in a molecule, but it's a different idea. You're actually trying to assign electrons, whereas the idea here is just counting covalent bonds, right? How many covalent bonds is this atom in? How many lone pairs does it have? We call it a charge because it can be either plus or minus, but really it comes down to just a reflection of what is the bonding versus non-bonding distribution of your octet or whatever number of electrons that atom has. Whereas oxidation numbers is a bit more of, hey, what if this molecule was actually ionic, right? It's a different idea as to where those electrons are. So we don't want to get these two things confused, but they are kind of fake charges we just make up about atoms and molecules that are serving a purpose. All right, so let's get some practice on determining the formal charge on all atoms in each molecule. So you'll notice we are just given a molecular formula. And so the first step is always going to be draw Lewis structures. We're going to get to the point now that we know how to use Lewis structures or know how to come up with them. Oftentimes we're going to be asked about a property of a molecule or of a compound, and one of the first places to start is always going to be drawing the Lewis structure, because that's going to indicate what the bonding is, and that's going to drive all of the properties. That's going to determine everything else from there. Plus, formal charges are formally a charge associated with atoms in a Lewis structure. All right, so we know formal charge. If we're asked for that, there's an associated formula, so we can always use that. Atomic valence electrons minus lone pair electrons minus 1/2 of the shared electrons. And then each uniquely bonded atom will have a unique formal charge. So if there's all the types of oxygen, get a formal charge. All the types of nitrogen, get a formal charge. So let's take a look at water. Water's Lewis structure is one we've looked at a couple times. So oxygen is going to be the first thing. 6 valence electrons. That just comes from oxygen. I can see that it has the 4 valence electrons across 2 lone pairs. I can just count those. And it has 2 single bonds. So each of those bonds, right, 1, 2, and each of those corresponds to 2 electrons. So 2 times 2 gives me 4 electrons that are bonding there. So if I want to put that into my formal charge, 6 minus 4 for the lone pairs and 1/2 times 4 for the bonds gives me a formal charge of 0. So oxygen usually forms 2 bonds, and it has 2 bonds and 2 lone pairs here. So formal charge of 0. We'll look at hydrogen, this first hydrogen over here. I can see no lone pairs. And so no non-bonding electrons, but it has 1 bond, and that is 2 bonding electrons. So the hydrogen has a full 2 electron valence. So its formal charge 1 minus the 0 lone pairs minus 1/2 times 2 gives it a formal charge of 0. Hydrogen almost always going to have formal charge of 0 because they just form 1 bond. There's never lone pairs around hydrogen atoms. So they just have a formal charge of 0. Hydrogen, again, my other side, I can take a look over there. Still one valence electron. I can see there are no lone pairs and the one single bond for 2 bonding electrons, and I get a formal charge again of 0. And it ends up that because both of these hydrogens just have a single bond, they have the same bonding pattern, so we would expect them to have the same formal charge. The atoms of the same type with the same number of bonds. And so in general, that's always going to be true. So we didn't actually need to do both calculations for the hydrogens because we can see that they're both hydrogens and they both just have a single bond. So we could just say hydrogen 0, right? All the hydrogen atoms are going to be the same pattern. CF2O, this is the Lewis structure we figured out last time. So we'll go through, we'll start with fluorine. We know fluorine brings in 7 valence electrons. That's totally independent of this Lewis structure, always true of fluorine. In this Lewis structure, it does have 3 lone pairs. That's 6 non-bonding electrons. And it's in 1 single bond, which is 2 bonding electrons. Okay, so it's got that. We plug that into a formal charge, 7. We take the whole 6 out of it, and then 1/2 of the bonding 2, giving us a formal charge of 0. So that works for this fluorine, and it's also going to work for the other fluorine. If we look similarly, it's just a fluorine with a single bond. So we know that it's going to have the exact same formal charge because it has the same bonding pattern. Same atom type, same bonding pattern. It's going to have the same formal charge. We only need to figure out the formal charge one time for whatever that atom is. So we could just say fluorine is 0 in this molecule. Okay, so let's take a look now at carbon. Carbon always has 4 valence electrons. Again, that just comes in, it's a property of the atom. It doesn't have any lone pairs. We can see there's nothing around this central atom, so there's 0 non-bonding electrons. It does have the 2 single bonds and 1 double bond, so single bond, double bond. We know each of the single bonds is 2, so it's 2 times 2, and the double bond is 4, so 2 times 2 plus 4 gives me 8 bonding electrons overall around that carbon. If I plug that into my formal charge, 4 minus 0 minus 1/2 of 8 is 4 as well, giving me a formal charge of 0. So again, carbon tends to form 4 bonds, and it formed those bonds. There's no informal charge. It doesn't care if it's double bonds or single bonds, just how many total bonds does that carbon atom have. In this case, 4, so it's all good. Let's look at oxygen now. 6 valence electrons. The 2 lone pairs give it 4 non-bonding electrons. Those are wrapped around up there. And there is, again, the double bond. So that's 4 bonding electrons. So if we look at that overall, plug it in, it has a formal charge of 0. So that gives us the fact that oxygen tends to form 2 bonds. So we can get our nice formal charge classification for all the atoms in here. So carbon is 0, fluorine is 0, oxygen is 0. And you know, one of the things when we did this actual Lewis structure, you know, we said that oxygen was going to be what lost its lone pair because of formal charge, right? Or because of electronegativity. Sorry, we said oxygen was less electronegative, so it was going to lose that electron. We can also now point to formal charge indicates that that's going to happen as well. If the oxygen had kept that lone pair with a single bond, it wouldn't yield a formal charge of 0, and one of the fluorines would then have a formal charge of not 0. And generally things want to have formal charges of 0. We can kind of classify down, you know, we want to minimize these formal charges, the magnitudes, because things want to follow their bonding patterns, their expected bonding patterns. Okay, ammonium, NH4+. Let's take a look at the nitrogen atom here. 5 valence electrons like normal. There's no lone pairs around that nitrogen. And it's in 4 single bonds for a total of 8 bonding electrons. So if we look at the formal charge, 5 minus 0 minus 1/2 times 8, that gives it a total of +1 for its formal charge. So formal charge of +1, and we can see this is where we're starting to get a first non-zero value, and that's because we know nitrogen usually forms 3 bonds and has 1 lone pair. So basically we can count this +1 as exemplifying the fact that this hydrogen has 1 more bond than we would expect. It has 4, right? It doesn't have a lone pair. Instead, it has satisfied its octet by obtaining 4 bonds instead of 3 bonds and a lone pair. And so it has, you know, it doesn't follow the expected bonding pattern, which is okay. It still has an octet. It's just kind of a way to signify this isn't necessarily what was expected. If we look at our hydrogen, we have 4 hydrogens. They're all going to be the same. 1 valence electron coming in, 0 lone pairs, 1 single bond for 2 bonding electrons, formal charge of 0. So, well, as we would expect, the hydrogens do follow the expected pattern of just that single bond. Like we said, the hydrogens always are going to. So if we take a look at these formal charges and we add them up, right, it's 1 plus 1 on the nitrogen and then zeros on all of my hydrogen. Overall, I get a formal sum of plus 1. And so one of the things I can see is that plus 1 sum of formal charges equals the charge of the molecule. So NH4 plus is a positively charged cation, right? And so if I sum up all the formal charges, it's going to become plus 1. So practically, that's one. This is a way to check your formal charges. We've gotten 0 on our 2 previous examples, and they were neutral. We've got 0 on everything. You add all those up, you get 0, corresponding to a neutral molecule. So you can always check your formal charges. You can add them up and make sure they match the charge of the overall molecule. The other thing, so that's kind of a practical, kind of tip. The other thing that's since ions have an overall charge, in ions, you tend to find atoms that don't follow their standard bonding pattern, right? Overall, the sum of formal charges had to be plus 1 on this molecule. And as a result of that, some of the atoms had to have non-zero formal charges. In this case, it was the nitrogen. So when you look at ions, or when you're working on the Lewis structures of ions, it's one of the most common places to see breaks in the standard bonding pattern. Nitrogen with 4 bonds instead of 3 bonds and a lone pair. Oxygen with 3, carbon with, that's generally going to keep 4, but say carbon with 3, phosphorus with more or less, something like that. All right, let's take a look at nitrate, NO3 minus. And so nitrogen, again, 5 valence electrons. It doesn't have any lone pairs again in this one. It does have some bonds. In this case, it has 2 single bonds, the 2 single bonds, 1, 2, and then the double bond. Again, that's 8 bonding electrons. And so if we take a look, we can get another formal charge of plus 1. Again, nitrogen tends to form 3 bonds, but here it's forming 4. And so, that's 1 extra bond. So it has a formal charge of plus 1. If we look at our oxygens now, we're not just going to have 1 formal charge on oxygen. And that is because there's 2 different types of oxygen. There's our double bonded oxygen and our single bonded oxygen. There are 2 single bonded oxygens, so those 2 will have the same formal charge, whatever it is, but it will be distinct from the oxygen that's double bonded because it's a different type of oxygen in a different bonding environment, so it's going to have a different value. So let's start with those single bonded oxygens. Oxygen has 6 valence electrons that it brings in. In this case, the single bonded oxygens have 3 lone pairs. That's 6 non-bonding electrons, and then they just have that single bond for a 2 bonding electrons. Okay, so if we look at the formal charge then, I get -1. And so this is reflected in the fact that oxygen usually forms 2 bonds. So this is 1 fewer bond than oxygen tends to form, right? Oxygen tends to form 2, and each of these just has that single bond. So -1 formal charges correspond to less bonds than expected. Then if we look at the double bonded oxygen up top, same 6 valence electrons going in as the other one, but we can see the distribution is different. I have 2 lone pairs for 4 non-bonding electrons, and then 1 double bond for 4 bonding electrons. So when I look at the formal charge now, I get 0. So that double bonded oxygen is lining up with what we would expect with 2 bonds on the oxygen atom, so it gets a formal charge of 0. So if I look again at all these formal charges and I add them up, the sum, I can have the nitrogen right there. I have the oxygens right there. Both of them are -1, and the doubly bonded is 0. So +1, -1, -1 plus 0 gives me an overall formal charge of -1. And that gives me the charge, matches the charge of my cation. It's nitrate, NO3 minus. So that's a good sign for my formal charges. So I have a little bit of positive, a bit more negative, and that comes out to 0 overall. So I've got this nice balance, and I can predict what's going on here. Okay, so formal charge, motivation, if we return, was the idea we were looking at resonance structures. And formal charge, the idea was we wanted to kind of answer this question of how many bonds does an atom tend to form? And that's exactly what formal charge looks at. And so one of the things it lets us do is it lets us quantify, which Lewis structures, which resonance structures or Lewis structures give us the best representation of the expected bonding. And so what we want is better Lewis structures overall have more formal charges of 0, right? We want low magnitudes. If I have a lot of +1s, -1s, all that kind of stuff, that means it's not really what I want. What I want is a formal charge of 0 on every single atom, because that means all my atoms have an octet and they have the right number of expected kind of bonding partners, distribution of bonds and lone pairs. So if I take a look at the CO2 molecules that I had, I have first off with the triple bond and single bond. And I know with that triple bond now, that oxygen has its own Lewis formal charge and it's +1, right? Reflecting on the fact it has one extra bond. And I can, it usually has 2, it has 3 in this case. The carbon is a 0 formal charge, and the other one, the single bonded oxygen, has a formal charge of -1. So that kind of indicates this isn't necessarily the best Lewis structure because I have formal charges that are non-zero. They overall add up to 0, reflecting the fact that it's neutral, but basically the electrons aren't balanced correctly. They're not distributed in the best way possible. If I look at the double bonding choice, both double bonded oxygens have a formal charge of 0, and the carbon also has a formal charge of 0. Because they are all 0 indicates that this is the best Lewis structure. Not only do all of my atoms have full valences and complete octets, they also are following their preferred bonding pattern. This Lewis structure over here with the triple bond and the single bond, I can draw it, and it follows all my octet rules and everything else makes sense. But because it has these non-zero formal charges, this bonding pattern is not reflective of the real molecule. A real carbon dioxide molecule is not described or characterized by any sort of triple bonding character in one side and single bonding on the other side. It is instead purely just double bonded across.